We're really happy to have Claude talk about fluctuations in conserved quantities at Alice. This is obviously a very important topic, especially once we go to higher densities, but to calibrate things in a very proper manner at high energies would be really, really good. And this is what we want to understand. And this talk will help us do that. And just a couple of official announcements. So typically, we don't take questions during the talk. If you have a very pressing question, you can write it in the chat box and we can take it quickly. But if it's a detailed question, then just wait to the end of the talk and we'll have some time to discuss those. So with that, the floor is yours. Go ahead, Claude.
Thank you, Rishi. Well, thanks for inviting me to give this presentation. And full disclosure, this will be my personal view of some of the measurements that were published in recent years by the Alice collaboration. And this is actually not necessarily the talk I would like to give. I would probably prefer to talk on what I've been doing most recently, be that as it, which is measurements of balance function and differential correlation functions. But there's quite a bit of interest in measuring these integral correlation functions or fluctuations. And so here we are. And so again, hopefully this presentation is useful to you. And what I try to do throughout the presentation, in particular for students, is to point out areas where there is a need for further measurements and developments. Okay, so just to to set the expectation, or to set the environment here, we are dealing with heavy ion collisions at very high energy. So what we think is happening is that we have two nuclei incoming. They're relativistically contracted, so they come at each other like pancakes, and as they collide, an enormous amount of energy is dissipated. This leads to a medium that we believe thermalize, at least locally, very quickly. And then with this thermalization, then there is a pressure within the medium that pushes the expansion of this system because there's a gradient of pressure in the three axes. This leads to longitudinal expansion, the fastest. And the second fastest is in the reaction plane. And this leads, of course, to very well-known anisotropic flow, which has, I believe, has been covered very well in your conference series or seminar series. And so we find that the system expands. And during this expansion, what we hope is happening is that some kind of a thermalized medium is produced. So at the canonical picture that we have is that at the onset of the collision, quarks are released, gluons are produced, and then the system expands for a finite amount of time. And the thinking is that during this expansion, the number of gluons in quarks is not changing very much. So we have a period of isentropic expansion. Eventually, the system cools down, of course, as it expands, and at some point, it can no longer sustain a QGP phase, so gluons are somehow reintegrated into hadrons. Additional quarks are made, and then you have the production of hadrons. Those interact perhaps for a short amount of time, and then eventually stream out into our detectors. And so what we really want to do here is focus on this time period of isentropic expansion that should tell us the properties, hopefully, of the quark-gluon plasma. And so this is a diagram which I'm sure is familiar to all of you. What we are trying to do here is to examine the properties of the quark-gluon plasma phase to determine these properties. And at the Large Hadron Collider, of course, we are in a region where the baryon chemical potential is almost vanishing. And so we really are at the left of this diagram. And matter, as it cools down, then has to come down to in temperature. And so it will eventually cross this boundary, which we now believe, based on LQCD calculation, is a crossover type transition. And so, what do we hope to achieve with the kind of measurements that I'm going to be talking about today? Well, ideally, we would like to understand and confirm that this transition is a crossover or second order or crossover. We would like to establish there is a deconfinement phase, perhaps even chiral restoration in that phase. And additionally, we would like to measure the properties of this quark-gluon plasma. And so that means shear and bulk viscosity, which is addressed very much from flow measurements. But there are properties that are also of interest that have not been covered as much. That includes the compressibility. In fact, Tapo Naik, who has joined this series, has been involved in a measurement by Alice that targeted the compressibility, but I'm not going to talk about that today. Then there are other properties such as the heat capacity and electric and color conductivity. So there's a lot of properties of this phase that have not been fully addressed yet. And essentially, we're still scratching the surface in our understanding of the properties of the quark-gluon plasma. So what do we hope to achieve? So, but let's before I go forward, let me emphasize what we actually know at this point. And so what we know at this point is that this QGP that is formed is essentially in a local thermal equilibrium. And in a thermal equilibrium, then we can use tools such as the grand mechanical ensemble with a partition function shown in the yellow box. And based on this partition function, then one can calculate such things as the pressure, the quark number density, the baryon density, and so on and so forth. An interesting aspect in efforts have been put into measuring susceptibilities of the quark-gluon plasma, or QCD at the phase boundary. And so this is these susceptibilities are basically nth order derivatives of this pressure, and it turns out that they can be measured, at least in principle, from cumulants of net charge, net baryon number, and net strangeness fluctuations. So I'll come back to that in a moment. So, but how do we know that we have something that looks like a thermal system? Well, this slide is somewhat busy. In fact, I have a tendency to have all my slides a little too busy. I apologize for that. But on the left and on the center panel here, I'm showing a comparison of yield or densities of particles produced at RIC on the left panel and at the LHC in the central panel. And so you see that so what is shown here is actually a comparison of the yield measured and the yield calculated based on hadron gas model. And we see that both at RIC and at the LHC, there's a very good agreement between the prediction and the data. And so this gives us some confidence that at least to first order, to a very good approximation, the system that we're measuring and producing and measuring are quasi-thermal or essentially thermal. In addition to this, we can also measure the temperature at which the system freezes out. And this is the curve I have on the right-hand side. I'm here talking about a chemical freeze-out. And in this particular plot here, it's compared to a calculation on the lattice of where should be the transition from this transition from the plasma to hadronic matter. And so from here, we find that it appears that the transition is happening almost at the same temperature as the freeze out, the chemical freeze out is happening. So this also gives us a inkling that to think that the matter that is produced is thermalized and essentially goes into hadronic matter very, very quickly. So whatever equilibrium was achieved in gluon matter persists in hadronic matter. And so what we measure in our detector should be a pretty decent signature of what was in the QGP phase. And so I was just mentioning that in particular in the context of the grand canonical ensemble, we can measure these susceptibilities defined here in the purple box. And the way this is done is by measuring cumulants of the fluctuations, delta n sub q, where q can be a charge, strangeness, or baryon number. And the relationships shown here indicate how these cumulants are connected to the susceptibilities. So cumulant of order 2, susceptibility of order 2, order 3, susceptibility of order 3, and so on and so forth. One of the caveat here, of course, is that these susceptibilities are the cumulants are proportional to the volume. So, and the volume is very difficult to establish. And so what has been done by measurements so far at STAR and in ALICE is to take ratios of these cumulants, and in these ratios the volume cancels out. And so in principle then ratios of cumulants are giving us ratios of susceptibilities. And so in principle this gives us access to some of the properties of the quark-gluon plasma. And one of the paper that I will be showing really focuses on this particular aspect. But more generally, why do we measure event by event fluctuations? Well, we can do a number of things. We can study the collision dynamics and the QGP signature. And in one of the measurement that I will be discussing is the magnitude of net charge fluctuation as a signal of the confinement. We can also measure differential probes such as balance function, and there we can, in principle, learn even more the diffusivity of quarks, baryon and charge stopping, and so on and so forth. From the thermodynamic perspective, evidently, we can now probe temperature fluctuations via transverse momentum. That gives us in principle, access to the specific heat. We can study multiplicity fluctuation, that in principle, that gives us access to the compressibility. And then we can study fluctuations of net charge, net baryon number, and net strangeness. And that, as I just showed, this should give us access to susceptibilities of the matter that is produced. And there is also a number of other things that one can do, but we won't have time to cover all that. So what I would like to do in the talk is give you first a quick reminder of the tools of the trade, what are the quantities that we use, and I will endeavor then to talk about net charge fluctuation, measurement of fluctuations of relative species abundances, measurements of fluctuations of net quantum numbers, in time permitting, a search for disoriental chiral condensate, but I really don't think I'll have time to cover that. So let's start with the mathematical foundation. And much of what I am going to be talking about here is actually covered by this book that I wrote that I published in 2017. So sorry for the sales pitch, but I actually did quite a bit of work to write that book. So I hope that it can be useful to the community. And so, first of all, the first tool that we have to be aware of is the notion of moments of order n, and centered moment, which I call delta x of order n. And so, if you have a system where you have an observable let's call it x, that fluctuates event by event, and this observable, the fluctuation are in principle described by some probability distribution, then one can calculate the moments of this observable x, and that's done through the calculation of the expectation value. So I'm showing here expectation value of order 1, that's the mean. expectation of order 2, that's the second moment, expectation value of order 3, that's the third moment. Now, as such, these are not particularly useful experimentally. What people tend to look at more is the so-called centered moment, where now instead of calculating just the second power or the third or the fourth power of x, you calculate the power of the deviation from the mean. And so this evidently in the case of the second order, that's the variance, and then the third and fourth moment of these expressions, and they are, as it happens, related to the skewness and the kurtosis of these distribution. Just to emphasize that M2, the second moment or variance, is telling us something about the dispersion of the PDF, whereas M3 tells us about the asymmetry, and M4 tells us a little bit about the shape. Now, if you're theoretically inclined, you may know already, or you should perhaps know that we can, given a PDF P of X, we can calculate something called a generating function, and we can then take derivatives of this generating function, and that gives us all the moments that I talked about on the previous slide. There's also something called a cumulant generating function, which is essentially the log of the generating function on the left. And again, here, by taking the derivative of this, we happen to find quantities that we call cumulants. And these cumulants are essentially related to the centered moments that I've talked about on the previous slide. And these cumulants are what people measure when they seek evidence for or the proximity of the critical point, or anomalies in fluctuations of net charge, net strangeness, and so on and so forth. And so, indeed, these cumulants, which are related to the moments, the simple moments that I've introduced on the previous slides, these cumulants are of interest because they can be at least nominally related to susceptibilities, and one can then get access through measurements of these moments to the magnitude of these susceptibilities, how they vary with the potentials, and perhaps also with the temperature. Additionally, the second moment of the multiplicity, as I've already mentioned a couple of times, that gives us access in principle to the compressibility of nuclear matter, but I'm not going to cover that today. Another tool to be aware of is what we call factorial moments in their generating function. And so if I, on the yellow box here, I'm showing particle densities, single row 1, pair of the pair densities row 2. And one can show very easily that by taking integrals of these density, we get at first order, we for a single particle density, we get the average multiplicity in a certain acceptance omega. And if we do this with a pair density, then we get the number of pairs in that same acceptance. You can do this for third and fourth and so on orders. Again, here one can introduce factorial moment generating functions, and the derivatives of this generating functions give us these factorial moments. Of interest also is what we call factorial cumulants. And again, here, factorial cumulants are obtained from the log of the generating function of the regular factorial moment. And so these cumulants are obtained by taking derivative of this generating function. And so what we get for a single particle is just the mean. For pairs, we get this expression here, and so on for triplets, and so on and so forth. Now, why do I talk about this? I talk about factorial cumulants because they are intrinsically, by construction, they're sensitive to the presence or absence of correlation. When we measure particle, we want to know whether they are correlated in the nature and the strength of these correlations. So factorial cumulant are ideal in that context because they enable us to have access to the information, whether or not the production of particle is Poissonian or purely statistical, or whether they are in fact correlations. And this is something the simple cumulants do not do. In that context, then it's useful I'm going to use that immediately when I talk about fluctuation of net charge. It's useful to introduce a ratio of second order factorial moment to a product of first factorial moment. And it takes this expression here. And again, so because the numerator will vanish in the presence of Poissonian fluctuation, R2 will also vanish. But if there are correlations, R2 will be non-vanishing. And so in the context of measurements that I'm going to be talking about in a moment, we have such things as a quantity called nu dynamic, which is a combination of these ratios, and the combination involves measuring correlating pions and kaons and so on and so forth. And so before I actually introduce the measurements, I have to tell you one more story about how these cumulants behave. Now, as I said, these cumulants are a measure of the intensity or the magnitude of the correlation. And so if you now have a system, AA collisions, involving two large nuclei, and if you can consider that the nucleons are colliding with each other independently, then the cumulants that you get out of a collision involving many binary or participant collisions, it will be something that I write as F sub n, the cumulant of order n, but for a collision involving m such nucleon-nucleon collision, if you will, and it's easy to convince oneself that this cumulant should be m times the magnitude of the cumulant for a single collision. And so so if we now put that into R2 that I'm going to be using for nu dynamic, what we find is that R2 then for a system of involving m collisions, it should be as it should go as 1 over m the strength of R2 for a single collision. So then that means that in the study of AA collisions, we can formulate R2 in terms of what would be expected for PP, R2 with a index 1 here, and we would expect that in AA it should scale inversely to the charge particle multiplicity. And so that means that in practice, if we now assume that the average multiplicity at given centrality is m times the multiplicity produced by PP collision, then that gives us an expectation that R2 has this relationship, and consequently nu dynamic that I will introduce a little better in a moment, as also this scaling with the multiplicity. And so that gives us then a way to study whether or not the system that we produce is a simple superposition of proton-proton collision, or it actually deviates from that. And so by scaling R2s or nu dynamic and plotting that as a function of the multiplicity, we can find whether we have a perfect scaling, which is what is shown here, or whether we have an increase or decrease of this quantity. So let's get to the first measurement. Net charge fluctuation, from this paper already published 10 years ago. So the context of this measurement is that, let's suppose that you have a box, and then you collide nuclei, and you look in this box surrounding the collision site, and in this box you have charged particles. They can be negative or positive, and then you count them, and you count the net charge inside the box. This net charge will vary or fluctuate collisions by collisions. And so what you would like to know is how the net charge inside the box is fluctuating. Of course, we're not measuring in coordinate space, we're measuring in momentum space. So as the system expands, whatever is in coordinate space then is streaming into a momentum box in rapidity space and PT, transverse momentum. So the point here that was suggested by a number of authors already 30 years ago, 20 years ago rather, is that if you have a QGP phase, the charges in the box would be 1/3, 2/3, plus minus 1/3, plus minus 1/3. Whereas if you have hadrons, you should have plus minus 1, essentially. And so that means that the net charge fluctuation inside the box should have a magnitude that reflects what kind of charged particles you have in the box. And so, so that gives us, in principle, a very easy way, or at least in principle, to find out whether we're dealing with a deconfined quark phase or we're still dealing with hadrons. And so there were many predictions, as I already stated. A lot of these predictions were formulated in terms of this normalized variance shown here, done omega sub q. But one of the important works that was done in particular by Sanyang and Volko-Kosh was to predict the magnitude of the fluctuation based on the ratio of the number of pluses and minuses. And they then turned this ratio into a variance of the ratio, which they connected to an observable that they call D, as defined here. And as it turns out, omega and D are related by the relationship shown in the orange box. So what was interesting about these predictions was that the magnitude of D should have three distinct values depending on what's going on. And so D should be of order 4 if the fluctuations are purely Poissonian. If we have a hadron gas, D would be of order 2.8, whereas if we have a QGP that hadronizes very, very quickly, then D should be of order 1 or even smaller than 1. And so that's, in principle, a pretty clear-cut distinction between QGP and hadron gas. So at the time, a lot of people got very excited about this prediction and set out to measure these fluctuations. So, so here on this slide, I'm showing a brief summary of some of the measurements that were done and what observables they were measured with. Together with my colleagues Sean Gavin and Sergey Voloshin, we came up with our own observable that we call new dynamic. I've already mentioned it. And it turns out that all these observables at some level are equivalent to one another, but we argued that it was beneficial to use new dynamic because it translates into the physics of the correlation between the particles. Let me show that. And so if I now take the observable by Volko-Kosh and Sanyang, this R, this quantity R defined in the yellow box, a value in a given event will have a deviation from the mean. And so then I can do the algebra here, define the average R as the ratio of the averages, and I can do an expansion and so on and so forth. And so at the end of the day, I can calculate the variance of R normalized by the square of its average, and you get the expression shown in the purple box. And we call that expression nu. And so what is the magnitude of nu and what does it mean? Well, first, let's look at what the value of nu should be in the presence of Poisson fluctuation. So if we have Poisson fluctuation, we have a Poisson distribution. The mean is mu, the variance of n will be as well mu. And so in the context of measurement of yields and multiplicities, what that means is that the variance should be equal to the mean of the multiplicity, whereas the covariances, in the absence of correlation, should give us 0. So if you then put that in the expression of nu that I had on the previous page, you find that it takes this expression. And so consequently, we have a Poisson limit for nu that is just given by what's in the yellow box. Now, this is not particularly interesting because there's no physics here. It's just Poisson fluctuation, just pure statistics, nothing interesting. So let's take that limit and subtract it from the expression for nu. And what we get is in the orange box. And what I'm showing in the orange box, I write it immediately in as a sum or combination of 3 terms, R2 plus plus, R2 minus minus, and R2 plus minus. And these have the expression shown in the yellow box. What this means is that new dynamic is sensitive to the correlation between positive particles, negative particles, and sensitive also to the magnitude of the correlations between plus and minus particle. So effectively, it is sensitive to the fluctuation of the net charge. And so to put that in context, based on the prediction by Falk and company, we found that for fast hydrogenization, we should have -3, hadron gas -1.2, and Poisson 0. So let's get to the measurement. I don't believe I have to introduce the Alice experiment. I'm sure other people have done that in this conference series. What I will just point out is that we have done this particular measurement based on the TPC, the internal tracking system, ITS, and we use V0 detectors for triggering minimum bias events. The net charge measurement that I report here is published in this paper. And I will just say that it was done from data collected in the first run, lead at 2.76 TeV, about 10 to the power 7 minimum bias lead collision. And what's important for this talk is that for this particular paper is that the rapidity range was plus minus 0.8, and the momentum range was 0.2 to 5 in order to really focus on what we call the bulk production of particles and sort of suppress the jets. And so here is the measurement. Nu dynamic is shown on the vertical axis as a function of the number of participants. And we find that, well, first of all, we find that nu dynamic is non-vanishing. It is finite. It is negative, which means that if you recall the expression for nu dynamic, it means that the third term, the plus minus term, dominates over the same sign terms. But we also find that the magnitude of nu dynamic is going down as we go from peripheral to central collision, and it's a very quick change. And so recall that I've talked about a trivial scaling of the magnitude of R2s in nu dynamic with the multiplicity. Can we verify that this is what's going on here? So to do that, we simply multiply the measured value of nu dynamic by this multiplicity. So that's what's shown on the right-hand side. We have the multiplicity times the measured value of nu dynamic. It's actually a corrected value, but that's a detail. And what we find is, what we find here is shown in blue for an acceptance of 1 plus minus 0.8, and in red for an acceptance of plus minus 0.5. And what you find, and I should also point out that at participant of 2, you have the signal from proton-proton collisions. And so you have a very smooth behavior. And what we see is that the magnitude of this scale goes from essentially minus 0.8 to minus 1.7, minus 1.8. And so there's a smooth change. And if you then look at what it means in terms of the D observable, you find that for a hadron gas, one would expect the values to be in this range of 3. So the data is giving us something below this range, but it doesn't quite reach the predicted value for a QGP according to the calculation by Falk company. We can also look at the scale nu dynamic as a function of the width of the acceptance that's shown here. And that tells us immediately that something is going on with this. There is a correlation land in rapidity. And you see that the magnitude of the signal decreases as you increase the width of the measurement. So in essence, it tells you that as you increase the width, it looks perhaps a little more like a QGP, but not quite. And so it wasn't clear what this meant, what we were missing here. It's clear that it was a little disappointing that we would not see a signal of a QGP directly, but maybe we were missing something. And the last thing that was done in the paper was to study the magnitude of the scale nu dynamic as a function of square root of S, and that's shown here, compared to star data and the points that we get in Alice. And so what we find is that it seems that as you increase square root of S, the size of the fluctuation is consistently going towards this QGP limit. But is that really what is going on here? I would argue that we were actually a little bit misled by ourselves. And so, so at the end of the day, the summary of this paper is that we have established that there are dynamic fluctuation. This sort of agree with a hadron gas, but we didn't quite see this these fluctuations go into the QGP range. Why? Well, maybe we were missing accounting for radial flow, diffusion. Maybe we had our expectation for the fluctuations were not right. And maybe maybe we did not take into account the fact that net charge is a conserved quantity. And so I'll leave it at that for now. I want to point out that there are many opportunities for new measurement. These fluctuations with new dynamic have not been measured at 502 in lead. They have not been measured in xenon. So there's plenty of work to be done here. Let's go to the next paper. Measurement of fluctuations of relative species abundances. And so here, the idea is that fluctuation of relative abundances may show critical behavior if we are near the phase boundary. And so the intent of this paper was to study the relative abundances of pions, kaons, and protons, and try to see if we could find evidence for manifestation of the crossover as an increase somehow of these fluctuations. And so this measurement was also based on new dynamic, and I'll remind you of the expression here, where now alpha and beta stands for either pions, kaons, or protons. And so this was published in this paper. So let's jump in and look at the measurement itself. Again, this measurement is again based on lead-lead collisions at 2.76. The kinematic range is slightly different, same rapidity range, plus minus 0.8, but a PT range that is slightly smaller, because here we require the identification of the particles, pions, kaons, and protons. And so that limits somewhat the PT range that we can examine. To be mentioned is that this particular analysis was done with a fairly novel technique of particle identification called the identity method, and I've included some references on this identity method at the bottom. I'm not going to talk about it, but if you were interested, we can say a few things at the end. And so the measurement is shown here as a table. I apologize for that. It's kind of a lot of information to digest. So the measurement of new dynamic are shown for pi k here, pi p, and pk. They're shown as a function of collision centrality. The centrality is obtained from the multiplicity in the V0 detectors, and the distribution is sliced into equal fraction of the cross section, or as shown here. In the second column is the multiplicity density found in the TPC. So let's look at pi k first. Well, we find that in most peripheral collision, pi k is of order 30, and it goes down to 1.35 in the most central collision. It is finite, always positive, but decreases sharply from peripheral to central. Let's look at pk. Same story. Pk is also positive always, and goes from approximately 20 to a fraction of unity in most central collision. Pi p is a little more interesting. It goes from a negative value of minus 16, decreases in magnitude, in absolute magnitude, but then changes sign midway, and then increases in value. And so this was a change of sign was not expected. It was a very big surprise. And so it means that if you consider the definition of new dynamic, it means that because there's a change of sign, it means that the magnitude of the cross term, R2 of the two species, changes size or magnitude relative to the same species, AA and BB. And this was not expected. If you just take this basic scaling that I talked about a moment ago, 1 over the charge multiplicity, the scaling should affect the 3 terms in the same way, so the sign should not change. So let's try to look at this a little further by now scaling with the multiplicity. That's what is shown here. So pi k in top panel, pi p, middle panel, p k in the bottom. And so let's look first at pi k. So this is again plotted as a function of the multiplicity or the density. And you find that the data are the red points. You find that the magnitude of new dynamic is positive always. The scale of new dynamic is positive. It somewhat increases in the most central collision, but not by much. Likewise for pk. And so again here, it's positive. It changed a little bit with collision centrality, but not by much. Whereas in the case of pi p, we see this sign change, which is really surprising. And so we see that it goes from a negative value, crosses at 0 around a multiplicity of 400, and then increases. And so this was not expected at all. But then can we invoke models to try to explain this? Well, we have simulations done with Hygiene, AMPT, 3 flavors of them. And the models are compared here with the 3 measurements. And you find that Hygiene and AMPT melting on and rescattering off and melting on and rescattering on, they're invariant with the multiplicity or the collision centrality, but they don't match the data at all. Likewise in PK, likewise in pi p. Interestingly enough, though, the AMPT version with melting off but rescattering on has a change of sign in pi p, but it's the wrong change. It starts positive and goes negative. So at the end of the day, what we find is that we have a surprise here with this sign change, but we really don't understand it. So this was also looked at as a function of square root of s that's shown here, but basically we really don't know what's going on. In particular, in the case of pi p, we see that there's this sign change as a function of square root of s. We don't understand what's going on at the LHC energy. So why is this evolution? We really don't know. And so this is an opportunity for theoreticians to really try to understand what is going on, to come up with better models to explain this data. And so the summary here, I've already said it. And so let's go to the next paper, net proton fluctuations. And so the context here is that lattice QCD makes prediction of second and higher order cumulants of net charge, net strangeness, net Bayer number. And in particular, this is done in the context of a search for the critical point of QCD in the phase diagram. And so a lot of measurements have already been done at RIC. Here, this shows you how these net charge, net kaon, and net proton fluctuates in this particular energy. Interestingly, this has also been, as I said, this has been a vast effort by STAR in particular to try to pin down the presence of a critical point. But that's for a different talk. But the point here is that even though we are at LHC and we're not likely to be near the critical point, there's still an interest to measure the magnitude of these net charge fluctuation. And that's the context of this paper. And to be more specific, at the time, there were LQCD calculation that signal that there is a pseudo-critical chiral temperature at about 156 MeV. And that corresponds to the freeze out of hadron multiplicities. And so basically the system goes from the QGP phase to the hadron phase very rapidly. And so we should be able perhaps to use the fluctuations of hadron to learn about the fluctuations in the QGP. And so in that context, there were predictions from hadron resonance gas, LQCD, and both these types of model were predicting that the fluctuation would be so-called scalan, which is in this context means Poisson fluctuations. And so are the fluctuations really Poisson? Let's examine this. To do this, I must introduce the notation used in that particular paper. They use notation kappa for cumulant of order 1, kappa 2 for cumulant of order 2, and these are defined as fluctuation of, so kappa 1 is the mean of the net baryon number, kappa 2 is essentially the dispersion or the variance of this net baryon number. One can further show that kappa 2 for the net baryon number is kappa 2 for the baryon, kappa 2 for the entire baryon, and adding a covariance for the number of baryons and antibaryons, which then leads me to say, well, if there are no correlations, if it's purely Poissonian, then kappa 2 then reduces to kappa 1 for NB, kappa 2 number of antibaryons reduces to kappa 1 for the number of antibaryon, and this covariance vanishes in the absence of correlation. And so that gives us a limit, which happens to be the so-called scalan limit. And so let's go on with the presentation of the measurement there. Again, same data set, 13 million lead-lead collisions at 2.76 TeV. Again, a slightly different momentum range, same eta range, but slightly different momentum range, 0.6 to 1.5. Again, here, because of the need to identify the particles, but also a need to suppress the contamination that for protons that happen at very low momentum. So, and again, here, this was done with the identity method. So here are the results. Kappa n plotted as a function of collision centrality. 0 is most central, 70 is most peripheral point taken in this particular measurement. You have in red kappa 2 for the net baryon number. I should stress that evidently we cannot measure all baryons, so we're doing this measurement just based on protons and antiprotons as a proxy to the number of baryons and antibaryons. And so in this case, we have kappa 2 in red for the net proton number to be compared to kappa 1, the sum of kappa 1s, so the so-called scalan limit of what is expected for kappa 2. We have kappa 2 for NP and number of antiprotons in blue, and we have kappa 1 for protons and antiprotons in green. And so what we find is that kappa 2 for the net charge goes down, as well as kappa 1, the sum of kappa 1s. And so it goes down smoothly, monotonically from central to peripheral. And then the question is, okay, how much does it deviate from scalan, from Poissonian type fluctuation? So this was examined using two ratios. R1 is kappa 2 of the net proton number divided by the sum of the multiplicity, and R2 is just kappa 2 divided by the multiplicity of proton. And so essentially the two ratios are really very similar to one another. So to cut to the chase, what we find is that if the data the system really behave as a Poissonian system or scalan, we would see that the ratio R1 and R2 are of the order of 1, but we clearly see a deviation from unity, and this deviation is changing a little bit with centrality, but not a whole lot. And so that indicates the presence of correlations. And so then the question is, what is the origin of the correlations? Now, PBM and collaborators, Peter Braun-Munzinger and collaborators, speculated before this measurement that the fact that protons and antiprotons, the net charge, the net baryon number should be globally conserved. They speculated that this should constrain the fluctuation and then make the fluctuation look non-scalan. And so let's go and discuss this a little further by looking at R1 as a function now. The opening of the measurement, the acceptance of the measurement, delta eta. And so 1 here means plus minus 0.5 acceptance, 1.6 means plus minus 0.8 acceptance. The data are the black points, and you see that at very small acceptance, the measured ratio R1 is consistent with Scalem, but as you increase the width of the acceptance, there's a clear deviation from Scalem, and overall, this seems to be somewhat of a linear dependence. Now, as I said before, this measurement was taken, PBM and collaborators had speculated that the global conservation of baryon number should imply that there is an overall correlation in the system induced by this conservation, and they came up with a relationship shown in the orange box where it should behave as 1 minus some coefficient alpha, where alpha was thought to be proportional to the ratio of the number of protons divided by the total number of baryons produced over 4 pi. And so this measurement then seems to corroborate that speculation that is done here with the red line, the red line. And so this model seems to corroborate what is observed experimentally. Case in point, if you do this with hygiene, you find that hygiene is completely missing the data. Now, so this was the view reported in the paper. I said at the opening that I would present my own interpretation, also in some cases, and I will take license to do that here. And so this is based on this work that I published in 2019. And so you can easily convince yourself that kappa 2 can be written in terms of factorial moments as shown here. And the Scalem limit of kappa 2 then is just the sum of the multiplicities, as I already mentioned. And then you can take the ratio of kappa 2 to the Scalem limit, and then it looks like what is shown here. I can then translate that into these R2 moment ratios that I introduced at the beginning of the talk and that we use for measurements of new dynamics. So we get this expression here, R2 PP, R2 P bar P bar minus R2 P P bar. And well, if you paid attention, you will recognize that this is new dynamic for P P bar. And as it happens, then the ratio to Scalem is 1 plus 1/4 the density of particles produced, the width of the acceptance, and the magnitude of new dynamic. And so that looks like 1 minus A times the width of the acceptance. So it's a trivial result that you should have a linear dependence with the width of the acceptance. The interesting component here is what is the magnitude of A? The magnitude of A, of course, will be dependent on the density of particles, but more importantly, on the magnitude of new dynamic. The fact that the slope of the red line is negative tells us that new dynamic must be negative. Now, what does it mean that new dynamic is negative? It means that there are correlation. It also means that this term, PP bar, is larger than the other terms. But this is intrinsically a measurement of correlation, not just fluctuation, but correlation. And so that means that there are correlation between P and P bar. Well, no surprise. You're making baryons, you're making baryon antibaryons. They have to be somehow connected in momentum space. And so how do we examine this? Well, then here I show you a measurement that is not a measurement of integral correlation. It's a measurement that we carried out in Alice and published in this paper. This was a measurement that my former student Jinjin Pan completed. And it's a measurement of what we call balance function. And we can define balance functions in a number of ways, but for the context of this particular presentation, it's interesting to look at balance function as defined here in the yellow box, where again it is the magnitude of the balance function will be proportional to the width of the acceptance, to the density, and then this combination again of the three terms R2, which you recognize again as something related to new dynamic. I will point out, however, that this is a differential measurement and it depends on delta y and then also on delta phi as it happens. And so shown here, just to illustrate how this works, is the balance function for pion and pion. So that means the probability, essentially the probability of finding a pi minus when a pi plus is produced, or vice versa, finding a pi plus when a pi minus is produced. And you see that this is near side peak very, very strongly. So the correlation, the magnitude, is a function of rapidity and delta phi. Similarly, for kaons, this is what we find in the central panel. And again, here you find that the correlation strength is large, but you will observe that the peak is very narrow compared to the pi peak. So there's some physics at play here that determines the width and the shape of this peak. Now let's come back to the proton-proton or PP bar. This is the balance function on the right of P and P bar. So what it means is that when I have a P, there must be an anti-baryon somewhere, a P bar, that balances and conserve the baryon number. And so this is what we see here. And so again, well, this was a measurement challenged by somewhat small statistics, so there's quite a bit of oscillation in particular in this particular plot. But what we clearly can see is that the balance function is very extended in rapidity, and it doesn't go to zero near the edge of our acceptance. So for pion, I'll point out that the balance function goes near zero, whereas for kaon, as well as for kaon, it goes essentially to zero, but for proton, it doesn't. So that means that within the acceptance that we measure, we are only seeing a fraction of this baryon balance. What is important then is to realize that the width of this balance function is very broad, which probably indicate that the correlation are very long range. And then we are seeing only a fraction of these correlation, and the fraction that we see is determined by the width of our acceptance. And so here, let me make my final point on this particular paper. And the point is that if you now take the integral of this balance function, you get what is shown in the green box. And so the integral of the balance function is proportional to the density of the particles, the width of the acceptance, and the value of new dynamic in that acceptance. And so what I've showed you is that our capacity to measure the balance function is limited. We are only seeing a small fraction of the balance function because it's very broad. And so that means that our capacity to measure new dynamic is limited by the acceptance that we have. And so now if I return to Schelem, this Schelem limit in the deviation from Schelem, you see the same phenomenon here, right? So if our capacity to measure the balance function is limited by the acceptance, our capacity to measure new dynamic is also consequently also limited. And so our capacity to assess what is the magnitude of these correlation is also limited.
It's 10 o'clock.
So that's an important caveat. It means that we don't fully understand the origin of these correlation. Perhaps it is sensible to say that they are determined by global baryon conservation. But if you look at what's going on for pions and kaons, it's clear that what dominates these is a local conservation. And even though PP bar is a little wider, it's clear that local conservation of baryon number probably dominates this phenomenon. And so there's quite a bit of work to be done to improve on this particular the measurement by PBM and company within Alice, but also the measurement that I'm showing here from balance function. And so, as I said, much to be done in PP, PA, xenon, lead. These measurements have not been carried out for this particular type of observable. And so there's plenty of opportunities for young students and postdocs to get involved. I was hoping that I could talk a little bit about search for disoriental chiral condensates, but I'm obviously completely out of time. So let me go to the very end here, just to summarize briefly. Whoops. And so I think, I hope I have given you a sufficiently comprehensive summary of some of the integral correlation and fluctuation measurements that were carried out recently by the Alice collaboration. And what is fair to say is that in all cases, the models fare very poorly relative to the measured data. As you saw, none of the models, or at least not Hygiene, not IMPT, in fact, none of the other models that are out there, be it RQMD or EPOS, have the capacity to explain the kind of measurements that are done here. And so that means that there's a lot of work to be done by the theory community, and lots of opportunities for interesting work to further our understanding of these collisions. I mean, I began my presentation by showing you that to a large extent, the particle production can be understood based on a thermal model in the context of a grand canonical ensemble. And so, yes, we have a good understanding of overall production of particle, but when we start looking into the detail at particle correlation, it's clear that we are missing something. We don't understand how the net charge fluctuates. We don't understand how the species fluctuate in abundance relative to one another. And we certainly don't understand how the net baryon fluctuates and how these balance functions take the width that they have. And so there are plenty of opportunities from an experimental side to enhance the data sets that we have and provide more data to the theoretical community. But I hope that within your theoretical community in India, there are people who can roll up their sleeves and take on this very difficult problem of accounting for charge conservation, baryon number conservation, and so on and so forth, and try to formulate models that are capable of explaining the data, having a better interpretation of the data, and yet addressing these conservations. Models like Pythia do that very well. They do that ab initio, but we also know that Pythia doesn't necessarily work so well with in the context of AA collisions. And so now we look for models that would account for charge conservation, baryon number conservation in AA. While you might think, what about models like EPOS? What about like hydro models? Well, as it turns out, these models are fantastic for the interpretation of anisotropic flow, radial flow, and so on and so forth. But because they use a Cooper-Freit prescription to hadronize the fluid, TMU, they do not account for local conservation of these quantum numbers. And so as such, they are bound to fail to reproduce the data that I have presented, and the data that, but hopefully the theory community in India and elsewhere can find ways of addressing charge conservation in these otherwise very good models. And so this is the end for me. I thank you for your attention, and I will welcome, of course, questions.
Thanks, Claude. That is very, very interesting. So I'll just open the floor for questions. Please go ahead. Either raise your hand or put your questions in the chat box. While we wait, I had a couple of questions. If you go to slide 29,
maybe there's more better way to do this.
okay, so Tapan also has a question. So maybe
29, here we are.
okay. I'll ask.
Yep.
Yeah, so I was wondering if one could calculate if there has been attempts to calculate new dynamic on the lattice, and suppose you put the values of the temperature and chemical potentials extracted from the fits to the yields and use those values to get these new core from the lattice. Do you have any idea if there's been attempts to see where they lie here?
That's a very good question. Now, on the lattice, you can calculate the susceptibilities, and then one in particular, you can calculate the susceptibility of the net charge corresponding to the net charge. And so that susceptibility gives you the magnitude of the fluctuation, and as such, it could be backtracked into the magnitude of new dynamic. Yes, and to be honest, I don't know where that would fall here at this point. Possibly not in what the so-called predicted QGP range shown on the slide, because this was a Benessian model that it turns out is probably not right. But to fully address your question, I should point out that when we did this measurement, and we did it in STAR as well, we came up with the notion that we should have a correction. And this particular measurement here includes that correction as per what's shown here. And the correction is 4 over the total multiplicity. When we wrote the new dynamic paper with Sergey Voloshin and Sean Gavin, we came up with this correction on the basis that, well, we didn't know how the effect of the net charge. We didn't know what the effect of charge conservation would be. And so we took a very pragmatic and simplified approach. We said, well, it should be on average, roughly speaking, the effect should be uniform across the acceptance. And so when you do the reasoning, you come up with this very, very simple ratio of 4 over n total. It turns out that this was not correct. It was not correct because now that we measure balance function, we see that the correlation between plus and minuses is actually very narrow on average. And so particularly when you talk about pions, I showed you the balance function, you saw that it's more narrow than the Alice acceptance. It's more narrow than the star acceptance. And so this correction then assumed that this charge balancing would be uniform over the entire range of rapidity, particle rapidities. And so this correction was really, really incorrect. Now, in the context of this measurement, is it a big effect? No. What is more important here is that it's clear that charge conservation, local charge conservation, is affecting the magnitude of new dynamic. And so, in fact, I showed you on one of those last slides on the balance function, the new dynamic is actually related to the integral of the balance function. And so the width, the shape of the balance function determines the value of new dynamic that we find in the acceptance. And so at the end of the day, what I personally, my own interpretation of this is that sadly, we cannot use this kind of measurement of new dynamic to assess the fluctuation that we would like to assess. So lattice calculates in coordinate space, and then the measure, and so you can assume that's what's going on in the collisions. So you have fluctuation in coordinate space, but then the pressure expands the system, and then it projects the particles in a momentum window, rapidity window. And what we see in this momentum and rapidity window is not so much predicated by the fluctuations in coordinate space, but predicated by charge conservation. And at the end of the day, that's we're kind of stuck with that. And so rather than trying to look at the magnitude of the fluctuation, we have to look at how the fluctuation evolved with rapidity separation or angular separation. And perhaps from there, we can tease out some information about the fluctuations in coordinate space, and then connect that perhaps with LQCD calculation. But or it's fair to say that our original thinking or old ideas were unfortunately not correct.
Okay, thanks a lot. Tapan, go ahead.
Hi, Tapan.
Yeah, very nice summary of the fluctuation results, Claude. And on this slide, in fact, we have in ALICE, we have the new measurements from 5.0 to TeV, lead, and xenon, proton as a function of multiplicity, as a function of multiplicity, and we measure D as a function of that.
Is that published?
Yeah, that paper is going to come up within a month or so.
Okay.
Working on that, but we're trying to finalize. There has been some systematics we have to finalize, so it's not yet done. We're working on the paper. So the final result which is coming out of that is that at 5.02 TeV, the results are not very much different from what we see in 2.76 TeV. I think most likely we all expected that, because what we see here, we see a difference compared to predicted hadron gas or the Poisson limit. That's clear. And also there is a difference from the predicted QGP range. And you rightly pointed out that prediction is probably has to be revisited based on our knowledge from local and global charge conservations and other effects. I think it's a very good opportunity to work on this kind of topic to see that. And your discussion on the balance functions in terms of delta eta, delta phi, and that actually takes one step closer to that. So I have one more comment about the net protons. We also have the net proton third moment published last year, and third moment is closer to 0. But the second moment, which is published for net charge and net strangeness, that all point to the local and global conservation. So understanding of the global and local conservation. So my question at the end is that, as you know, in ALICE 3, we are going to increase our eta window from plus minus 0.8 to plus minus 4 unit of rapidity. And I think one of the delta eta, one of the result which you showed, D as a function of delta eta, where you try to see things are going down and not saturating or not converging back. So maybe as a function of eta window, that might help in future in measurement, but that's quite a bit, many years from now. So in the meantime, if we have a good understanding of the theoretical aspects, Rishi's help and his group's help on this, on the lattice calculations, that would be really nice. So if you have any suggestion on that, Claude, yeah, thank you.
Thank you for your comments, Tapan. Yes, I completely agree with you. I would argue that with the measurement at 502, new dynamic is not very different, because unfortunately it's entirely driven by the shape and the width of the balance function. And just because the energy is increasing doesn't mean that the width of the balance function will change a whole lot. There are effects associated with radial flow, perhaps also to a lesser extent an isotropic flow, but by and large it should be a radial flow, and that will make the balance function a little more narrow at higher energy, because there's a little bit more pressure, a little more of a push. The average PT of the particle is a little higher. And so, so I'm not surprised that I haven't followed that particular analysis. And so I didn't attempt to present here because of, you know, the rules of the collaboration, but I'm not surprised at all. But your comment about Alice 3 is spot on. I think I would argue that with Alice 3, then we will become able to measure these correlation over a long range. And that we will be able then to do this with plenty of statistics, with much lower PT thresholds. And so there's plenty to be learned there. And there's in fact quite a bit to be learned. We can learn about the diffusivity of the system. We can learn about the history, the evolution of the system. And in particular, if we do this with PP bar, the question when we deal with protons is how much stopping is there, and what is the mechanism for the stopping? And so by measuring fluctuations of the net proton or balance function of the net proton, we will be able to figure out what much better than what we can do now. What are the mechanisms for this stopping? You know, what is carrying the baryon number? Is it really the quark, the gluons? This is a question by Karziev and others. And so we will be able to address that kind of question much better with Alice 3. And perhaps one last comment. When people look at higher moments, I am concerned that the same story may repeat. When we look at higher moments, we become sensitive to the balancing of charge. And so if you start with two pluses, right? Imagine that you have a string or a color tube, whatever you want, your favorite model is. And so you have two particles in one side, they must be balanced by two negative particles somewhere. And so this balancing them will constrain not only the second moment, but the third and the fourth moment as well. And so before we can claim that we really understand all of this, we have to be able to figure out what is the role of charge conservation in these correlation functions, in these fluctuation measurements. And I don't think we're there yet. Well, I think we're getting there, but not quite.
Thanks. Debashish, go ahead. Debashish?
Hi,
sorry,
Debashish.
can you hear me?
Yes.
Yeah.
Okay, sorry.
A little bit of static, but
Yeah. It's very nice talk. I mean, we have been discussing offline for quite some time. So I would like to bring back to the issue of small systems. So how, so again, that topic which has been baffling me for over quite some time, that even in your small systems, I mean, you showed one PP result, right? So how robust are these non-new dynamic or balance function variables in deciphering this whole plethora of the multiplicity stuff which we have been advocating, that there is a QGP-like behavior? I mean, it is more sort of a philosophical thing to me for now, that how do we pinpoint that what should we look there? Because, you know, whatever you have said is the recipe for the heavy ions. But now that when we have so much of data coming in for this round 3 in PP, and how do we utilize this interesting statistical variables to look into these small systems, or what is your take on it?
Right. So so they're instrumental aspects, but I will leave those aside. From a perspective of what's going on in PP and whether or not there's a QGP, unfortunately, it's very difficult with variables such as new dynamic to really assess that. Certainly, one thing that wasn't done so far in PP is to look at the magnitude of new dynamic or the kappa 2, as shown on this slide, as a function of the multiplicity in PP. So if we, one thing that I would suggest, and this is something that I find very, very promising and potentially very interesting. There are now people coming up with a notion of flatnicity. Flatnicity is a little bit like an event shape variable that says, well, when the event is very flat, there are no jets. We can be sure that, if the flatnicity is in a certain range, there are no jets. And so if indeed we can select proton-proton collisions with very few jets or negligible amounts of jets, then we would be dealing only with multiple particle interaction, MPIs. And if we then focus on the large multiplicity collision, then perhaps we would be dealing with a QGP, right? And then we can measure these observable in the context of PP collisions without jets, because if we cannot eliminate the jets, the jets themselves must conserve charge. You start with one quark or one gluon, and therefore everything that goes on into the jet must be a balance. A plus must be balanced by a minus, and so on and so forth. And so removing the jets, because the jets have their own dynamics, their own specificities, which are not that, interesting in their own rights, but for the purpose of QGP physics, not particularly in this context. And so if we could somehow select collisions that would have very few jets or no jets, then it would become possible to study these variables, these types of fluctuations in PP as well. And then compare what happens when you change the multiplicity in PP, and does it suddenly turn on, turn off, and so on and so forth.
Yeah. So I think you want to say that we have to somehow remove the jettiness or something like, or make a sort of a variable which will take out that sort of high PT structures out of the event, and then just look into the soft sector actually. But if you go into the very low PT in high multiplicity PP, will that be a safe zone? I mean, just looking into
well, the problem with low multiplicity PP is that you are, well, first of all, you're not expecting to have a QGP there, and you're entirely dominated by energy momentum conservation as well as net charge and net baryon conservation. And so whatever correlation you have in low multiplicity PP will be entirely driven by energy momentum conservation as well as charge conservation. And so I doubt very much then that we could exploit these observables here to learn anything about that would be tangible about the presence of QGP there. However, that said, if you have your favorite model of elementary interaction, it could be tested. I mean, these observables are relatively straightforward to measure there, and with very high precision. And so you can get very good measurement of what's going on in PP, whether low multiplicity or high multiplicity. And then that gives you a very discriminating tool to examine the models, such as Petya or Herwig and so on and so forth. And you will find that these models are about right, but they actually fail in the details.
Yeah, actually, I just wrote a review. I mean, it's just to educate myself. So, and there I found that whatever exists in PP is very small. And I tried to compile them, and I recently got it published. So that was a training for me, because that there is a lot of deviations going on from the Pythia and other stuff. So and also there is a need for this community to figure out a variable, which is what you have said about platonicity or something, so that we can use that, or many others, because the data which will come, where we will have the opportunity to look into the high multiplicity domains. That's what is my question. Okay, thank you very much.
If you're interested, there was a talk by a Texas University of Houston student at the winter workshop in nuclear dynamics that just took place a few weeks ago. If you're interested, I can send you the talk.
Okay, sure. I will contact you. We have been chatting.
I think there's still a little bit of work to learn how to do this properly, but I think it's promising.
Okay, yeah. And also this, I don't want to bring this stuff now, but we have been discussing a couple of days back about this charm fluctuations. So that stuff will be also important as we have seen in the Alice 3. But again, that may be probably a bit challenge here at this stage.
Well, I mean, it's as I said in my email to you yesterday or 2 days ago, I forget. There was work done already in Alice by the Lund group, Peter Christiansen and his students, and they already looked into correlation of charm particles. I think that's again here. This is a very exciting work that they have done. They're barely scratching the surface. Obviously, charm is rare. It's difficult to measure. But with Alice 3, we will have much more data at a much wider acceptance. And so it will be indeed possible to measure charm much better. And so one of the many questions can be answered. When is charm produced? Well, it should be early. Is there a recombination? And so on and so forth. So many questions will be addressable based on correlation functions or integral correlation functions, differential or integral.
Thank you.
Okay. Yeah, so you have to leave very soon, I think, for your class. So
yeah, I can. If I drive fast, I can I can answer a few more questions, of course.
So that's Subhash, go ahead.
Hi, Claude. Thanks for the nice talk. So I have question your slide number 30. When you discuss the net charge fluctuation with center of mass energy, we see that with increase of pseudo-relativity window, the fluctuation decreases. So, here the Alice result is inconsistent with the HRG limit, with the theory prediction. Suppose I measure it for delta eta, let's say 10, and my value is in between, suppose less than 1. Do I still call it QGP?
Well, what I was trying to say here is that one has to be very careful to how we interpret the data. I mean, it's clear that in the dependence that we see here, there are several effects. One is the magnitude of the charge is decreasing as you decrease the acceptance. So it appears to go Poissonian at very small acceptance. It's not necessarily Poissonian. There are correlations there. It's just that in this particular observable, you don't see them. Now, at larger acceptance, then according to this extrapolation here, it seems to max out. Really, the better way to do this is to measure a balance function or correlation function, because then you see the shape of the correlation. And you find that the shape of the correlation is largely determined by, well, there are a few things that will determine the shape of the correlation. First, the presence of resonances, hadronic resonance decaying into the particles that we measure. Second, how, as you collide nucleons and quarks or partons, they form strings, and then these strings will stretch and then decay, and then they lead to correlated particle production. And so the width of the balance function then is an indicator of how the string stretch and hadronizes into particles. And if the nature of the string is changing in central collision relative to peripheral collision, then some people have described or have been able to describe the production, the smooth increase of strangeness and charm from PP to AA by making fat strings, so to speak. And so by making fat string, you change the nature of the string, you change the string tension, and consequently, you also change the width of the balance function. So in principle, it's all in this measurement here. And so that's very, very, very interesting. But I personally advocate that instead of measuring integral correlation, you have to measure differential correlation function, because you have more sensitivity to the width and the correlation length of the phenomenon. sadly, when you do an integral correlation, that a lot of that is gone. A lot of the information is lost.
I see, but we try to measure this experiment, do this in CMS, but it is not any dynamics corrected. So for the uncorrected result, we see that our results for delta eta 4.8 is within 1 to 1.5 QGP limit. So I'm wondering if, suppose in future we increase the pseudogravity window and the value go beyond, means less than 1. So do we still call, means theory people suggest that if the value in between 1 to 1.5, it is QGP limit.
The short answer is the short answer is I don't think so. Nu dynamic is the integral of the balance function. When you increase the width of the acceptance, you capture the entire integral of the balance function. So the magnitude of nu dynamic will saturate. It will reach a maximum determined by the balance function itself, or the correlation length itself. And so at that point, nu dynamic at some point saturates. But if you keep increasing the acceptance, and charge doesn't saturate, you will, within your acceptance, you will see more and more and more particles. And so nu dynamic times and charge will keep growing. And that's probably what we see here on the right-hand side. You know, this is, at this time, it's a speculation on my part, but I believe that's what's going on.
Claude actually doesn't, I have done some calculations where in fact, it goes back again. It goes in this scale, it goes to about 3 to 3.5 or 3 to 3.4 and turns back again. So at this large delta eta window, this quantity becomes 0. So that I have shown in one of the publications.
Oh, you mean the corrected value?
The encharged nu dynamic corrected. Yes, the corrected.
Yeah.
The uncorrected doesn't grow. You're right. The corrected goes back again.
That makes sense. Yes, because the corrected attempts to remove the effect of charge conservation, and obviously when you reach a very wide acceptance, you kill the fluctuations, right? You have to match every plus to every minus. There are no fluctuations. And so, I think what you say makes sense. Yep, I understand. Yeah.
So, Subhas, you can check that actually.
Okay, yeah.
So I guess maybe if you have time for one more question, Raghunath has one question, and then I think we'll have to stop. Go ahead, Raghunath.
Yeah, hi, Raghunath.
Yeah, hi. So I have a query, not a question actually. So in one of your initial slide, you have shown that the number of quark production versus time, right? So where you have shown the up and down quark and strange quark and gluon.
Yeah, something like this is a very qualitative cartoon, actually.
Yeah, actually, my query is like you have shown here that the up and down quark production is larger than the S quark production. But is this true in this high energy? I mean, so I mean it is true for higher like charm and bottom top, but for S quark also, is this true? It's not same as up and down.
Yeah, that's a good question. Thank you. The logic, as I understand it, is twofold. You have two periods or two stages of quark production. The initial stage at the onset of the collision, the protons are coming at one another at a TeV scale energy or momentum, and so yes, at that point, it probably doesn't matter what the S quarks have a larger mass than the U quarks, and so my cartoon here may not be completely accurate. So maybe the S quarks are produced as abundantly as the U quarks because the mass may not matter all that much. However, when you reach freeze-out time, shown around 7 Fermi over C here, which is, again, that's a cartoon, not necessarily what's really going on, So at that time, now the system has been expanding for a while. The density has gone down, but more importantly, the temperature has gone down. And so now you want gluons colliding with one another to form S quarks. And so the energy available to make S quarks is much smaller than the onset. And so because the S quarks are more massive than UD quarks, the expectation is you can make much fewer of them. And so that's why in this cartoon, again, it's just a cartoon. The U and D go up, whereas S quark go up just a little bit.
Thank you.
But I'm not a theoretician, and this is not attempting to properly characterize the production. You have to do this in detail. You have to account for a number of degrees of freedom for each of gluons and quarks and so on and so forth.
Yeah, thank you.
Okay, thanks a lot, Claude. Hope to see you sometime, and that's it.
Maybe
bye.
We'll see each other at Quark Matter in September in Houston.
Sure. Yeah, possibly. Okay.
All right. Thank you
Thanks,
for your
everyone.
attention. Thank you for your questions. Goodbye.
Thank you so much.